Welcome to the lecture on mass conservation equation. So, we will be talking about the governing equations, especially the conservation equation of mass in this lecture, and we talked about the certain points related to the fluid fundamentals. And now we will be talking about the conservation equation for mass. So, there are certain assumptions in that we take the fluid as the continuum. So, basically for the analysis of fluid flow at the macroscopic length scale, so when it is 1 micrometer or larger, the molecular structure of matter and molecular motions we have to ignore for this analysis. Then we are also having the behavior of the fluid, which we try to describe in terms of the macroscopic properties like velocity, pressure, density, temperature, and their space and time derivatives. So, we are going to have these properties, and in that term we are going to have the discussion about the flow behavior or fluid behavior. Now, fluid particle or point in a fluid will be the smallest possible element of fluid whose macroscopic properties are not influenced by individual molecules. So, with this we are going to have the analysis of the flow behavior, and we will be talking about the conservation properties, conservative principles for certain things like mass or momentum. So, in this lecture we are going to talk about the mass. Now, if you talk about the properties of the fluid, so suppose you have a point x, y, z where you are defining. Now, in that case all the fluid properties are function of the space and time. So, you have properties like density, pressure, temperature or velocity. They are all said to be a function of space as well as time. So, we define it as rho x, y, z, t. So, there will be a function of the space coordinate as well as the time coordinate. Similarly, pressure also function of the space and time coordinate. Then you have the temperature, that is also function of space and time, and similarly the velocity. So, if you try to have the properties to be found at the faces. So, this is at the, suppose you are taking a cubical element. Now, in that this x y at x y z point you have these properties like these density or pressure or temperature or velocity. So, if you have to define at the face, so that can be done by the Taylor series expansion, and in that assuming it to be very small, you can ignore the terms which are coming after the first two terms. So, if you take this face, so that will be your west face on this side. So, on this face you will have if you take the pressure. So, if the pressure P is at this point x, y, z, so at this face it will be P minus dou P by dou x, and this will be half of delta x. So, delta x is the the length of this whole face, whole length is delta x, and this point has the distance of delta x by 2 from this west face. So, it will be P minus dou P by dou x into half of delta x. Similarly, pressure at the east face will be P plus dou P by dou x into half of delta x. So, that way you are going to have the you have to go to define these properties of the fluids at the different faces. So, similarly, when you go to the this north face, so you will have a P plus dou P by, so this direction is your z. So, this will be dou P by dou z, and then it will be half of delta z. So, that way accordingly you will have the value of these properties across these faces, and that will be used when we talk about the conservation principle of the mass. Now, coming to the mass conservation principle tells that you will have the rate of increase of mass in fluid element. It will be same as the net rate of mass into the fluid element. So, whatever net rate of mass flow is there into the element, it will be same as the rate of increase of mass in the fluid any element. So, what we see, as you have seen, that you will have at this point, if the these properties are u, rho, t, u, v and all that. So, or p, so that will be, you will have the values on all these sides, and we will have the expression for this accordingly we will be trying to find. So, the rate of increase of mass in the fluid element. So, rate of increase of mass in fluid element. So, it will be dou by dou t, that is rate of increase with respect to time, and mass will be density into volume. So, volume will be delta x, delta y and delta z, that is cubical element. So, density will be rho, and then you will have delta x, delta y and delta z. So, it will be dou rho by dou t into delta x, delta y, delta z. So, that is being a constant, it will be coming out. So, dou rho by dou t, delta x, delta y, delta z. Now, we need to have the value of the mass flow rate across the faces of the element. So, you will have the 6 different faces, and you need to find out the mass flow rate across these faces, and it will be given by, so mass flow rate across the face so that will be the product of the density. So, that will be rho, then you will have the area, and that will be further multiplied with the velocity component normal to the face. So, you will have the velocity component which is normal to the face, and then you will have density and the area. So, if you take the along the boundaries, so you will have the values, and if you see, it will be rho u. So, if you say you are taking the east face or so, so it will be rho u minus dou of rho u by dou x, and as you have seen, you have the half delta x. So, that is your the part. So, this is and then you will have this is multiplied by delta y, delta z, and then it will be so one is this and another is on the right hand side. So, it will be rho u plus dou of rho u by delta x, half of delta x, and that will be multiplied by delta y, delta z. So, if you take that in the x direction, so you have one flow from here and another flow on this side. So, that is what you are getting this these two faces, taking into account this terminology is coming. Similarly, you will have if you take the v component. So, you will have rho v minus dou of rho v upon dou y, and that will be multiplied by half of delta y. So, and that will be multiplied by again delta x delta z, and that will be further minus of rho v plus dou of rho v by dou y half of delta y, and it will be multiplied with delta x delta z. So, that will be for the y component, and then you have the z component. So, that z component will be again w will be coming. So, you will have rho w minus dou of rho w by dou z, and that will be multiplied by half of delta z. So, one is this multiplied by delta x delta y. Similarly, you have rho w plus dou of rho w by dou z half of delta z, and that will be multiplied by delta x delta y. So, this is the basically net mass flow rate that is across the phases. So, you have the rate of that is net rate of mass flow into the fluid element. That is what you are seeing from here. So, one is coming and another is going. So, net rate of mass flow into the fluid element will be this particular value. So, if you are taking, so in that what you see, you will be getting these terminologies cancelled, and you will get certain terminologies. So, here you are getting dou rho by dou t into delta x delta y and delta z. Now, in this case what you see, this is minus of dou of delta u upon dou x half delta x, and that will be minus of dou of delta u by delta x into half delta x into delta y delta z. So, these two terms will be added, and there will be a negative term of minus of dou of dou u by dou x delta y delta z. So, that is what you are getting. So, and this will be term ultimately together, and that will be equated to this term. So, what you get is that you are getting this term dou rho by dou t delta x delta y delta z. That will be equal to this term dou of rho u by dou x, and then you will have this delta x delta y delta z. So, it will be equal to a minus of dou of rho u by dou x delta y delta z. Similarly, minus of dou of rho v by dou y delta x delta y delta z, and similarly you will have another term that will be a minus of dou z of rho w delta x delta y delta z. So, that is coming as the negative term when you add all these terms of this. So, it will be minus and minus. So, it will be that half delta x will be delta x. So, delta x delta y delta z. Now, this you can write. So, delta x delta y delta z can be cancelled on both these sides. So, you can write dou rho by dou t plus dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w, that will be equal to 0. So, this is what you get. So, this equation, that is what you are getting, that is known as the conservation of mass. This is known as the mass conservation equation. Now, what you see, so this if you try to write in a compact vectorial form. So, in vector notation you can write this as dou rho by dou t plus div of rho u. So, that will be equal to 0. So, that is also, this is also known as the mass conservation equation. Now, this is known as the 3-dimensional mass conservation equation. Or we can also call it as the continuity equation. So, normally that is generally defined for the compressible fluid. However, if you have the incompressible fluid where density does not vary. So, in that case rho will be constant. So, for incompressible fluid, so when we talk about the fluid flow like water or steel, or so they are incompressible in nature. So, in that case the rho is basically constant. So, as the rho becomes constant, so your term becomes div of rho u, that will be equal to 0. So, this is the equation that is known as the continuity equation for the compressible flow. So, you simply write, in that case the rho becomes constant. So, rho will come out. So, div u equal to 0. So, it will be dou u by dou x plus dou v by dou y plus dou w by dou z, that will be equal to 0. So, that is what the continuity equation is defined as. Now, next thing what we will so next we will be studying about the momentum conservation, and before that we need to know something about the rate of change of the following the fluid particle and for a fluid element. So, that is capital D by dt. So, d phi by dt for any fluid property. So, that will be rate of change. So, that is total derivative basically. So, that is following a fluid particle and for a fluid element. So, you will have the changes in the properties of the fluid particle, and for that Lagrangian approach is used, and each property will be the function of the position and the time. So, all the properties being the function of the position and time, so x, y, z and t. So, we normally you have any property per unit mass which we define. So, we define, so suppose let we the value of a property per unit mass be phi. So, if you are seeing that phi, so it will be depending upon, so its value will be depending or will be depending upon x, y, z and t. And if you talk about the total derivative or the substantial derivative, that is capital D by dt. So, total or substantial derivative, so that is basically represented by d by dt of phi of any property. So, that d phi by dt will be represented, that will be equal to dou phi by dou t plus dou phi by dou x into dx by dt plus dou phi by dou y into dy by dt plus dou phi by dou z into dz by dt. So, this is the expression for the substantial derivative, and this will be used when we will talk about the conservation of properties like momentum or temperature in those cases. Now, for a fluid particle which is in the flow, so your dx by dt will be u and dy by dt will be v and dz by dt will be w. So, this will be your u, this will be v and this will be w. So, you can write d phi by dt, that will be equal to dou phi by dou t plus u dou phi by dou x plus v dou phi by dou y plus w dou phi by dou z. So, you can further write this as first is the transient term, that is dou phi by dou t, and then you will have the term that is you can write u grad phi. So, that is how u grad phi. So, it will be you have 3 components u v w. So, accordingly u dou phi by dou x plus v dou phi by dou y. So, this basically d phi by dt, it will be defining the rate of change of the property phi per unit mass, and that way we are going to use it for for expressing whenever we are going to have the definition for the conservation of mass equation or for the conservation of momentum equation. So, in that case we are going to have the use of these property phi in the different manner. So, if you talk about the mass conservation equation, so if you talk about the mass conservation equation, you will have mass per unit volume is basically rho. So, that is the conserved quantity. So, in that case if you talk about the change of the density, so sum of the rate of change of the density in time and the convective term and the in that mass consecutive term. So, if you talk about the conservation equation for the mass which you have derived earlier, that was dou rho by dou t. So, this phi will be basically replaced by rho. So, it will be dou rho by dou t plus u times grad rho, and since rho will not be changing. So, accordingly you can see here that was div of rho u. So, that is what you can get it from that particular equation itself. So, if you try to have this for the arbitrary conserved property, you can write the generalized term, that will be dou of rho phi by dou t plus div of rho phi u. So, if you try to derive the conservation equation for either the mass or the momentum, you can directly get from here. Now, if you see that if you look at the expression, the dou of rho phi upon dou t plus div of rho phi u. So, that will be if you see, it will be rho of dou phi by dou t plus u grad phi plus phi times dou rho by dou t plus div of rho u. So, that becomes equal to rho of d phi by dt. Now, in this case what you see that the term, that is phi times dou rho by dou t. Now, this term is 0 because the density is constant. So, that term becomes 0, and also plus div rho u. So, that this term becomes 0. So, what is coming out of this expression is that when you see the rate of increase of any property phi of a fluid element, so that is your d phi by dt substantial derivative, that will be net rate of flow of phi out of the fluid element plus rate of increase of phi for a fluid particle. So, accordingly you can have, so if you look at the momentum equation which we will try to derive, in that you will have the term for x momentum, y momentum and z momentum. So, if you look at the x momentum term, now in that case you will have the different terms. So, you will have the term u, you will have rho du by dt, and accordingly you will get dou of rho u by dou t plus div of rho u u. So, that will be for the x momentum. Similarly, if you go for the y momentum, you will have the velocity component is v. So, you will have the total derivative rho dv by dt, and that comes as dou of rho v by dou t plus div of rho v u. So, accordingly, so this way you will have the z momentum equation, and in that you have w. So, it becomes rho of dw by dt, and that becomes equal to dou by dou t of rho w plus div of rho w u. So, accordingly if you use this total derivative term, this total derivative total derivative or substantial derivative expression, that will be used for finding these conservation equation for momentum also in the coming lectures, where we will be having the derivation of these conservation equation for the momentum. So, in the coming lecture we will be having the expression for the momentum equation in 3 dimension. Thank you very much.